Alright, so now we've jumped over to Unity, and first we're going to take a look at what we're actually going to create. So we're going to use a cross product to actually determine how to generate geometry to show a path that the user decides to pick. So you can imagine that if you were designing a game where you have some sort of tactical or stealth implementation, maybe you have to choose the path of an individual at the start of the game, you need to show the user, the player, what path they've chosen. So in this case, we have a white plane in the background, and as you start clicking, you just place a game object down. I happen to have an eyeball from the other project with the dot product we did. But then as soon as you place 2 points, we have a mesh that is a polygonal information automatically created for you, connecting these two elements together. So as you can see here, I can pretty much place them anywhere, and it starts generating the mesh for me. This is all possible thanks to the cross product. So what we're actually drawing here is not a line, but instead 2 triangles that form a quad, or basically a rectangle. And the rectangle spans from one button click to the next button click. All right, so here we are inside of a new scene in a project. First thing we need to do is add something to intersect with. That is a plane object. So let's go to 3D object, plane, reset it if it's not already at the origin. Scale that plane object up so it's much larger than just a 1x1. And the next thing we need to do is modify our camera. By the way, the plane object already comes in with a mesh collider, meaning we can do collision checks against this object. So let's go to main camera. We're going to rotate the camera so it actually looks down instead of up. The idea is we're kind of looking at from a RTS perspective vertically over our entire area. Make sure the rotation is set to 90 degrees. The next thing we're going to modify is we're going to change it from perspective to orthographic. So with an orthographic camera, you'll notice that instead of being this sort of frustum or truncated pyramid going outwards, it's instead just a box. The reason for this is because orthographic views preserve the dimensions of an object. That is, as an object recedes into the distance, it isn't divided by z. An object isn't divided by z with an orthographic camera, which means it doesn't get smaller as it goes off into the distance. But we do have a few problems. First of all, the camera is right on that plane, so let's raise it up a little bit. The second problem is that it's too small. I wanted to see a much larger area of my mesh, so I'm going to increase the size. And then our far and near planes are a little bit wonky. The first thing is that it can look up to 1,000 units below this, which is way beyond what I need. So I'm just going to modify this. Let's make this, I don't know, maybe 200 instead. Let's see, it's not quite far enough. As you can see, it's now not able to see anything. I'm just going to bring it down a little bit so it actually intersects that area. All right, so now we have our camera set up, we have our plane set up, and it's about time for us to start generating our paths. Create, C# script, please. There we go. Call it Path Manager. There will only be one script in this project just to make things simple and clean. It's going to be attached to our camera object, just making it easier to access the camera information. So let's go ahead and click it. Let's go ahead and grab the Path Manager object, drag it onto our main camera, as you can see here. Perfect. Go ahead and double-click Path Manager to open it up either in MonoDevelop or Visual Studio based upon your editor preferences. So there we are, it's open. This is of course inheriting from MonoBehavior because it's a component type in our scene. So the first thing we're going to do in this is set up clicking on the screen and finding an intersection against that plane with the mouse, and then placing an object there and storing that point. And then once we've done that, we're going to get into drawing that dynamic mesh between those elements. So let's go ahead, and first we need a reference to the camera object. The camera is what's going to let us do some of this testing. I'm going to create a new method, void awake, a magic method inside of Unity. So this will happen as soon as this object becomes initialized. Let us get a reference to that camera. So let's do camera is equal to, no, don't do that to me, is equal to GameObject.getComponent of type camera. This script is going to assume there's a camera object on there, so I want to use the require component, parentheses, type of, and then use camera. So it requires that there's a camera component attached to this object. So if we come back in here on plane, on main camera, we'll notice that nothing changes because there's already a camera object on it. But if we were to go to Path Manager and drag it onto the plane instead, what you'll notice is the plane now has a camera component on there. That's what required does. Remove that now. Oh, I'm sorry. Let's remove the entire script first, because Unity yells at us saying that that script has to have it, so you can't do that. So the next thing we need to do is start registering where the user's clicking. We're going to perform that in the update method. Easiest way to do this is to just do an if statement and check whether or not the mouse has been pressed. Or what I like to typically do is get mouse button up. The idea is that after the up is done, you've kind of committed where you want that to be placed. If you press down, a lot of times user wants to slide it around and maybe get a chance to alter where that location is. So we'll do if get mouse button up, mouse button 0, which is the left mouse button in this case. So just so I don't have a name clash with Unity's camera, I'm going to just type cam. Unity reserves or already implements a cam object as being a variable in case you happen to attach one. I don't like to use those default ones because they can be a little bit more expensive for it to find that object. So let's not do that right now. So I renamed camera to cam. Now what I need to do is grab the location of where the mouse is on the screen. And that's done with input.mousePosition. Now that's going to be a vec2 object. So now we use the mouse position to convert it from a 2D object, that is a screen position, to a 3D point in our actual world. We need the camera to do that. The camera has a function called screen to world point. That's going to take in the mouse position and return to us a vec3 object, a point that has basically converted it from this position to a point on that near clip plane right on the screen. We're going to save this value out as vector 3. We'll just call it world chord. The idea is we've gone from our screen space to our world coordinate space by calling these functions. It's basically a nice way of saying an intersection test. To do this, we first want to store a raycast hit object. This object is going to store information during an intersection event. The next thing we're going to do is create a ray object. So the ray is a vector, which is the direction, as well as a point that it starts at. So we're going to do new ray. And in there we pass in the location, which is going to be world chord, and then now the direction that we're looking at. Now, in our case, we're attached to the camera object and the camera is looking straight down. We can use the camera's forward vector, or that is the game object's forward vector, to determine what direction we're looking at. So let's do game_object.transform.forward. Now because we're looking straight down, you could have also just used vector3.up and multiply that by a -1.0, which causes it to go down instead. That could be something you use, but this is better because if we ever change the camera's angle, this will be that camera's angle. We don't have to come back in here and change anything in the future. Okay, so now we have a hit object, which is going to store information once a hit has been registered, and then we have a ray, which is going to be what we use to test whether or not there's been a connection. Okay, so I just caught a quick error. So in this case, I have camera, which is the class name. This is not a static method. It's not class-wide. It's for each instance of the camera. So I just want to replace that with cam. Sometimes autocomplete can be a pain. Let's come back in here. I should no longer have any errors to work with. If we go to our camera object now, we have a location in our inspector to hold a transform. And that's going to be our plane object, which I'll drag in there. You could have also searched for it using a tag and given it its own tag if you wanted to, or found it by name. It doesn't matter. This is just quick and easy for us. Okay, so now that we have this, let's do the intersection test. So now that we have a container to store the raycast hit information, as well as the ray we're going to be using when we want to do the intersection test, we need to do a raycast. Now you can do a very general raycast, which is using physics.raycast, but you're testing it against all objects in the scene. We only want to test it against one thing, and that's that ground plane. So why not just only test it against that? Now to do that, we need a reference to that object. So in our case, what I'm going to do is raycasts are performed using the collider object. And in this case, I have a mesh collider on that ground. So we're going to do mesh collider, ground collider. All right, and I need to make that public as well. So now let's come back in here, go to our camera, and we'll see that we have a ground collider object right here with nothing in it. So let's drag that plane object into it. Now it automatically knows to attach the collider to that object based upon its type, its class type. So we have access now to that ground collider. We're going to do ground collider.raycast. Now there's a lot of different ways of doing a raycast. The way we're going to do it is by first passing in the ray, and then we're going to hit out, which is the keyword telling us that we're going to get information back, put in hit, and then of course the maximum distance. This can be a value you can change by putting it in the inspector as a public variable. I'm just going to do, I don't know, 200, something like that. I'll have to check what our distance to that plane object actually was, but that's probably fine. Raycast, if you take a look at the returns a bool value. So we can use this in an if statement. And the idea is that if there is indeed a raycast and that it hits something, now we can perform something on it. That is, we can look at the hit information. So if we type hit dot, you'll notice you get all kinds of things, such as the normal or direction of the surface that you hit, the point itself, which is what we're going to use, rigid bodies, textures, all kinds of wonderful things. So in our case, what we want to do is create a new function that's going to handle adding a point into our mesh. So let's call add point, and add point is going to take in just a vector 3, which is going to be hit dot point. Now that's the exact point where we struck that surface. So now let's go ahead and create that function. Let's do, this can be protected. No one else needs to call it except for us. Protected void, add point, and then in add point, we're going to want to make sure we take in the vector 3 object, which is just going to be called point. So within point, what we're going to do is, I wanted some sort of an object to show up on the screen wherever you click. If you want to, you can make it a plane, a sphere, or anything you'd like. In my particular case, I happen to have an eyeball from the previous dot product project that we were working on. So first I need to reference that object though. Every time I click somewhere, I want to place an instance of that game object or that prefab. So I'm going to put in a public field, game object, and let's just call this prefab point. So every time I click somewhere, I'm going to create an instance of this object. Let's go ahead and set that up. So like I said already, you can use a sphere if you want to. So here it is, prefab point. If I click that right there, I'll get a list of any of the game objects I currently have that I can work with. I'm going to use an eyeball for my case. You can use whatever you want. Just make sure you've generated a prefab. You do that by going to game object, 3D object, cube, create one in the scene someplace, and then just drag it into your project. And now you have a prefab of that cube to work with. And if we go to main camera, I have a eyeball as my prefab for this project. Let's zoom in a little bit. We're way out there. Actually, I made things way too big. I'm going to kind of zoom us back into that surface. Take a look at the game view. Everything looks fine, it looks like, right? Now that we have our prefab attached to the object, every time I click somewhere, I want to create an instance of that prefab. Now, I don't just want these prefab objects to be littering up my hierarchy that is over here in this panel. I want to control them, contain them by making them child object. We can use game objects like containers. Boy, we're covering a lot of topics in this video, but anyway, we'll get to the cross product in just a few moments. I wanted to make sure I gave you something interesting. So let's do a public game object, and we'll just call this point parent. Sounds like a good name. In the awake function, we're actually going to generate that object. So let's do point parent is going to equal a new game object. Just at the origin, no problems there. We just want a container to hold all this stuff. Now in add point, what I want to do is create an instance of that prefab. Now when you're dealing with prefabs, you don't just call new, you actually have to call the Unity instantiate function. So we're going to call instantiate, and then of course we say the type. We're going to create a game object, and then what we're creating an instance of. We pass it a game object, in this case prefab point. I'm going to save that over. Game object gm is equal to instantiate. So that will create an instance of that object. The next thing I want to do is make that a child of our parent object, the guy containing all this stuff. So let's do gm.transform.parent is going to be equal to the prefab point.transform. The next thing to do is move that object to wherever we clicked. So we want to do gm.transform.position is going to be equal to our point. So now, let's go ahead and save this, come back in here, check for any errors, nothing yet. Let's go ahead and run this. So here we are. So now I'm clicking in, oh, I noticed a problem. Check this out. We're not adding these to the new game object. And this is telling me right here that I'm actually trying to add this to the prefab object. So let's go fix that. Looks like I just made a quick typo. If we come up here, you'll notice that, oh, here we are, prefab point. I shouldn't be adding it to the prefab. I want to add it to the point parent. That's what happens when you use names that have the same starting bits. You get a little confused. Okay, so now if we come in here, go ahead and run, clear out everything, and hit start clicking things, we'll notice that our objects are now children of this game object. Just keeps things tidy and clean. All right, so now we've got all of our points. What's up next? Well, we need to connect all these points together. So we're going to generate our own mesh, and this is where we're going to use the cross product to create thickness to our line. We already know how to make a line. We take each point and we just draw it from one to the next. But if we want thickness to that point, that is thickness that's oriented with that line, right? 90 degrees offset at all spaces, that's where the cross product is going to help us out the most. So I'm going to create a new function. I'm going to call this regenerate mesh. Now I'm going to warn you right now, this is not the optimal way to do this. This is the way that's easy to understand and is perfect for what we're doing here. Normally I would not be regenerating the entire mesh with each button click. I would just be adding to that mesh each time. All the other points are already calculated. I don't need to fiddle with their values. But in this case, we're just going to go through all the points that we click and recreate the mesh every time we add a new point. So let's go ahead and create that function now. Do it right here. Once again, this is going to be a protected function. I don't need to let anyone else access this. We'll call it regenerate mesh or create mesh or whatever you want to really call it. Now the first thing we need to understand is we need to see if we have more than one point. But wait a second, we're not storing points anywhere. Oh, that's a problem. So the first thing I need to do is make sure I store all of my points. So let's create a list object to do that. But first I need to using system.collections.generic, so I have access to this class. Now let's create a public list. It's going to hold our points, which are vector3 objects, and I'm going to go ahead and call this points. In awake, I'm going to want to make sure I, of course, point is going to be equal to a new list. And it is going to be composed of vector3 objects. All right, so we've initialized our object right there. All right, so now we've created our list to hold the points. Within add point, we can go ahead and give it a point. So let's do points.add, and we'll add to it whatever point was passed in. Within regenerate mesh, which by the way needs a return type of void, the first thing we need to check is to see whether or not we have enough points to draw anything. So I want to do an if check, if points.length, dot count is greater than 1, draw it. Why? Well, because if I only have 1 point, I can't exactly draw a line. So now that we've done that if check, I need to make containers for the vertices of my objects, the indices, as well as the coordinates that I'm going to generate, UV coordinates, so that we can texture this object. I want to put a nice little arrow on it to indicate the direction that we're moving in. So let's create a list of vertex objects, which is going to be a list of vector3s. That is going to be not the points, but offsets to the sides of each point to construct our triangles. Then we need an indices list. The index list is the connect the dots portion. It tells the computer how to connect them together, how to build lines or how to make those triangles, what dot is connected to which one in what order. And then we're going to need a UV coordinates list. The UV coordinates are going to give us the ability to add textures to our object and to project those textures onto the surface properly. So I'm just going to make these class objects up here. So let's do a protected list of vector3s, and we'll call this vertices. Do a protected list of integers, which is going to be our indices, and then a protected list of vector2 objects. And that's going to be our UV chords. Now you'll have to wait for one of our future videos, which is going to be about texturing, where we actually explain what UV coordinates are all about. So just kind of understand that UV coordinates usually are in a range between 0 and 1, and it's how you put an image onto the surface. It's what part of the image you're sampling, basically. So now that we have those, we can come in here, and every time I do this, I'm going to reset my list for right now. So let's do vertices is equal to a new list of vector3. Now I could clear this list each time if I wanted to as well. It's entirely up to you. Doesn't matter a whole lot to me, to tell you the truth. Copy that a couple times, change the insides to be of type int, and then of course to be of type vector2. This is going to be indices, and this is going to be UV chords in this case. Yes. Oh, I spelt it wrong. I thought so. change that name, save it. All right, so now we have our lists of objects. Now I want to iterate over every single point. So let's do for, nice big for loop. I don't want to start at the first element. I'm going to start at the second element and then look backwards all the way up to the end. So we're going to do int I is equal to 0. You could do the opposite of this by starting at 0 and going all the way to 1 minus the end. But in our case, I like to start at 1. Just makes more sense in my brain. We continue processing until I is less than the number of points, .count, and of course I++ with each loop. All right, so the first thing we need to do is create a vector that connects our first point to our second point. So let's do vector 3 direction is equal to points I minus points I minus 1. Now, if you follow along in those other videos I put up about vectors as well as a dot product, this should be familiar. This is a vector going from point I minus 1, which is 0 at the start, to point 1, or the next point. What I want to do is normalize this. I only want to use this as a direction. Now that I've normalized that value, I'm going to calculate, using the cross product, a side vector. That is, I want to know what vector is perfectly 90 degrees off to my side. Because I'm dealing with a plane, I know things are perfectly flat. So in my cross product, I'm going to cross it, the direction vector, against the up world vector. So let's do vector 3. Side vector is going to equal vector 3 dot cross. And within cross product, it's going to be the direction, and I'm just going to use vector 3 dot up in this case. So if you remember from our example, we did something very similar. I believe it was the x and the y, and we did the z. In this case, we're doing the z and the y value, so we're going to get an x value, or a value off to our side. Now I need to scale this side vector by how much I want to move over to the left and to the right, and we're going to add a new public variable that we're going to call width. And that's just going to say how big it is, or how wide we expect our lanes to be, times 0.5, because we're going to have two side vectors, one that goes to the left and one that goes to the right. So we're in the center right now, so we want to only go half the distance. So let's add a new float, public float. So public float width, I'm just going to set that equal to 2.0f at the moment. So that means we'll actually create a lane of width 4. Now the next step is to create the 4 vertices that make up this object. I'm going to put a diagram off to the side. So we have the center lane going down the middle, which is our vector, our direction vector. And then we of course have this now side vector, which gets us off to the other side. So to calculate those points, if we take point I minus 1, and of course add the side vector as well as the side vector times -1, we get off to the left and to the right. And if we do the same thing to the top point, to the left and the right, we'll get those 2 points. So let's do that. So let's create vector 3. P0 is going to equal points I minus 1 plus the side vector. Copy this. Create our next set of points, P1, P2, P3. Now for this one, it's going to be points I minus 1, and then we move up to the top part of this, so it's just going to be I. And instead of side vector, it's going to be side vector times -1.0. To flip it, times -1.0. Remember, if you don't know what this is doing, go back and watch the vector math ones I've already put up. Now, those are our vertices. So let's do vertices.add. We're going to add each of these. So P0, P1, P2, and P3. Perfect. So now we need to tell the computer how to connect these. That is, here's a diagram over here. Now, this is a little complicated. We're not going to get into it right now, but there's a thing called winding order, which is used to determine the direction of the surface. If you input these in wrong, what happens is you might not see your object. You might actually have to rotate your camera and look under it because it might be facing the wrong direction. Okay, so if for some reason you don't see anything after trying this yourself, you probably have your winding order wrong, and you need to just kind of change from from counterclockwise direction to clockwise for Unity. So actually, something that's even easier for us to just do really quickly is to put in our UV coordinates. So for each vertex, we need a UV coordinate. So let's do UVCoords.add. Point 0 is going to be 0, 0. That is, point 1 is going to be the rightmost bottom of the image. Point 2 is going to be the top right, and then point 3 is going to be the left top of that image. So let's do new vector 2. 0.0f, 0.0f. I'm going to copy this line. 2, 3, 4. And now we're going to go to the right, which is going to be the x direction. Now we're going to go up, so we're both over 1 unit and up 1 unit. And now we're going to move back, and we're only going to be up in the vertical. UV coordinates are a discussion all in of themselves, so don't worry too much about that part. So now up, we just need to explain the order, and we need to add indices. So we're going to do indices.add. So like I mentioned before, you have to be very careful. We need to construct our triangles. That is, for every triangle we create, we need to specify 3 indices. A triangle has 3 sides, 3 points that define it, so you need to define those 3. What I need to do is take I minus 1, multiply it by 4, and then because of my winding order, I'm going to start at 2. But let me just finish this first triangle, then I'm going to explain it to you exactly what's going on here. So in my world, in Unity's world, I need to go counterclockwise, if I remember correctly. No, I'm sorry, clockwise. OpenGL is counterclockwise. So I need to go clockwise. And with how I've laid things out, going from 0 to 1 to 2 would be the wrong direction. I need to go from 2 to 1 to 0. But what about this funky math I'm doing over here? Well, I'm creating a giant array of information, all right? And I need to tell it which vertices to use. So I need to say, okay, at the first triangle, I want to use vertex 2, vertex 1, and vertex 0. So if you think about this for a second, when the first loop we're going through, I is going to equal 1. 1 minus 1 is 0. 0 times 4 is 0. So I'm telling it to use vertex 2, 1, and 0 in that order. Now the next time I come back here, the next triangle, I need to make sure I'm 4 more vertices than I was before. So for a value of 2, it's 2 minus 1. That gives me a value of 1 times 4. So now I know I need to go 4 vertices past that first triangle, and then I need to add 2 to it, 1 and then 0. When you learn to make your own procedural meshes, you need to learn how to think about how things are counting, how you're specifying which point needs to be used in a procedural way. So it does take a little bit of getting used to it. But if you just sit there and with a pen and paper and start doing the math in your head, or on scratch paper really, don't do it in your head. I used to do this all the time, especially with terrain generation, where we had to do some pretty funny things with triangle strips to get terrains to draw on one single draw call. Anyway, back to indices. So now I want to do the next triangle. Same thing, I minus 1 times 4, because there's 4 vertices in each set that I'm doing. Now I need 0, 3, and 2 in my case. And I'll have a diagram over there of the winding order so you understand why I'm doing it that way. Now that we've generated our indices, our coordinates, and our vertices, it's time to plug this stuff into a mesh filter. I want to put all this stuff on a new object. I actually don't want it to be on my camera object because I don't want my camera to move around and have this as child objects and things just get all messed up. Let's create a new game object just to hold all this information. That is the mesh filter and the mesh renderer. So protected game object paths. In Awake, we're going to generate that game object just using new game object. Scroll on down. Now the first thing we're going to need to do is, actually that's a blank game object. So the first thing we really need to do is add to it a mesh filter and a mesh renderer. When you create a generic game object, it's just a transform. It has no other components. So let's do paths.add component. And we're going to do mesh filter. Once again, if you haven't already, look at my other videos where I do this. I explain it very clearly what the mesh filter and the mesh renderer do. But while I'm typing, I might as well tell you. So the mesh filter is going to hold all your vertex, index, and so forth information. The mesh renderer uses the mesh filter as well as material information to finally render it to the screen. So now we have those attached to that object. In a perfect world, I should really save these values out. I'm going to keep accessing the mesh filter and the mesh renderer in the future. So yeah, I should store these away so I'm not constantly looking for it using expensive Unity calls. So let's do protected mesh filter MF. And we'll set MF equal to that mesh filter. Mesh render, I don't really need to worry about at the moment. So let's go to MF. So now I need to create a new mesh. So we're going to go mesh is equal to a new mesh. So now that we have a new mesh, we need to populate it with vertex, UV, and index data, as well as normal and other stuff, but we're not worrying about it in this video. This one's going on long enough. So let's do mesh.vertices is going to be equal to our vertices that we calculated, mesh.indices, mesh.size, set indices is going to be equal to our indices. The next parameter is our topology. That is, what kind of geometry are we constructing? For us, we're creating triangles. And then the last parameter is going to be our submesh parameter, which is just going to be 0. Ignore that for now. Next up, we need to set the UV coordinates. So let's do mesh.uv. You can have multiple UV coordinate slots. We're only using one, so let's do UV coords. And forgot this, but we need to convert all these over to arrays. Unity expects arrays. It is not going to work with a list, so just add the .toArray to each one of those. And now all we need to do is tell our MF mesh filter that its mesh is now equal to the new mesh that we generated. And that should be it for creating the information on the screen. Let's go ahead, check for any errors real quick. Looks like we have one. Double click. Can't convert from a float to a vector 3. So in this particular case, I do side vector is equal to my width value. So this is wrong. I want to do side vector times equals the width times 0.5. The idea is I'm scaling that side vector by this floating point value. That should clear that up, no problems. Perfect. Let's go ahead and hit run and start drawing on the screen. Not seeing anything, let's take a look at the scene instead. And we'll see what the problem was. So we were drawing that geometry directly on top of this surface, making it impossible to see. Now, an interesting thing is, it looks like I have flip-flopped some of my stuff. So you'll notice that if I'm on the top, this side is thick. If I go to the bottom, this side is thick instead. So this is exactly what I was talking about with winding order, and this is very easy to fix. It just means that if I scroll down to where I do my calculations, where I'm adding these indices in, I made a quick error and I'm just doing the wrong order. So we can either adjust our order here, or we can adjust the order of which points we're actually constructing up here, in which order they're at. So in my case, I'm going to swap this order. I had done things a little bit backwards. So let's do this, copy that there, and there we are. This way, it's more like a square we're moving in. We're going from the one side and then over and then up and then back over again. Stop this, run it again. Place some points really quick. Check out our scene. Move this down slightly. Now there's a couple ways you can fix the fact that it's being drawn right on top of it. The way we're going to do it in here is we're just going to introduce a slight offset value so that it's always being built above the surface. You could also, if you get proficient enough, write your own shader to adjust the Z depth of an object, or you can mess around with the render order of objects as well. But that's not for today's discussion. So let's just create a generic offset vector. So in this case, every time I'm calculating the position that this thing should be created at, that is these points right here, I'm going to just pop that vector up a little bit in the air. The easiest way to do this is I could just add it to the side vector if I want to, but to just show you what's going on here, I'm going to add it to each of these points. So the idea is here's my final location. I'm just moving it up in the Y direction ever so slightly. Come back in here, hit run now. And now you can see all of my lines going perfectly where they're supposed to go. Now, of course, we can start drawing funny shapes. Come back over here and we can see it's ever so slightly above the surface of this object. So we have a problem, and that's that it's this ugly, funky purple. And that's because if we go over to our main camera, actually this game object, if we click on that, we'll take a look at our mesh renderer. What we're going to notice is we have no material associated with it. So let's fix that really quick. Let's create a new material. And let's just call this path material. So I made a texture really quick that looked like an arrow in Photoshop. I'm just going to add that to my albedo. This object gets generated at runtime. So if I drag that material onto this object, as soon as I turn this off, nothing's going to show up. It's going to reset itself and go away. So I need to do this in my code. More importantly, though, is I need to go to this. Let me see. Arrow is transparent. This one is not set up to do transparency, so I'm going to make sure I go from opaque to, let's do cutout. Yeah, cutout looks good. So now we have some transparency going on. So the easiest way to fix this is just to create a public material. And let's call this path material. Down here, where we're actually setting things up, where we've done our add component mesh renderer, I can, MR is equal to, let's just do mesh renderer. The mesh renderers dot material equal to path material. Come back in here, hit the run button, start plopping down points. Didn't work. Let's figure out why. So let's go to our main camera, and it's because I didn't associate that material with the object. So just drag and drop that in right there, hit the run button, and there we go. Now, if you want to get more sophisticated, you can use the length, the magnitude of this object to make the arrow repeat over and over and over again. Right now, every time I click here, it's only drawing the area in the image between 0 and 1, which is the full image. But if you increase that beyond 0 to 1 and make sure inside of your arrow you choose your wrap mode to repeat, you'll be able to draw multiple arrows along that one direction. So the arrows don't look all, really long and weird when you specify long paths all over the place. So I really hope you enjoyed this. I know it was a kind of a long example, but I wanted to do something that was, a little bit more creative and interesting, and something you might be able to put into your own games right now. I mean, it would be very easy now to use this and some of the dot product stuff we showed earlier, as well as some of the path, the seek and follow stuff, to make enemies now or allies move along these paths in some sort of an RTS or tactical game. So remember to like and subscribe if you enjoyed this content. I use that to determine what series I'm actually going to work on. Remember also to comment, tell me what you liked or didn't like as well, and I'll use that and change how I do things in the future. Once again, thanks very much. Hope you enjoyed it. Bye.